Yay!
Yay! There's another cool variation we can do based on our current loop. What we did maybe a video or two ago was to integrate stacked loops to form a solenoid. So we got the magnetic field inside of a solenoid just by integrating these loops, these rings, if they're stacked on top of each other. But now let's do something just a little bit different. Now let's do loops of different sizes and let them sweep out a disk. So this example is one that's popped up in a number of books that I've seen, and it's a disk of charge. Maybe it's an insulating disk, so the charges sort of stay in one place, but then you spin the disk. And so all these charges are in motion, and then they generate a magnetic field, right? So what we want to do is try to find what the magnetic field is along the z-axis, along the axis through the center of the disk. So what we're going to do is split the disk into a whole bunch of little current loops, little rings, and then we'll integrate them from 0 all the way out to R, right? The size of the disk. Okay, so the first thing we need to do is once again write down what the magnetic field of a loop is. So the field of a loop, let's see, what was it? Mu naught I times R squared. The size of the loop is little r, right? So let me leave it as little r. Mu naught I R squared, and then I want to say it's 2 times R squared, Z squared plus R squared to the 3/2. There we go. So that's the magnetic field of one loop of size little r. What we really want is these are going to be infinitesimally thin. So this is just going to generate a little bit of magnetic field. And so for a little bit of magnetic field, I'm going to do the usual thing where we're going to call this like dI, because as I spin it, it's going to generate just a little bit of current that's going to all add together. All right. So how are we going to do it? We're going to have to be kind of clever. Okay, what is a little bit of current? Let's work on that part. A little bit of current is going to be related to the amount of charge that's in that little ring. And we've already done this part. A little bit of charge compared to the charge in the whole disk. So that's a little bit of charge in the ring compared to the charge in the whole disk. And we said that's like the thickness of the disk. I'm sorry, the thickness of the ring compared with the area of the disk. The area of the ring compared to the area of the disk. There we go. I'll get it right. Okay, what's the area of this little ring? Well, it's going to be the circumference, 2 pi r, times its thickness, dr. And then what's the area of the entire disk? Pi big R squared, like that. So that's our little ratio. And why we're going to do this is because we want to be able to switch variables. We want to be able to express dI and dq in our magnetic field, dB, and then integrate them all. Okay, so once again, because I think I screwed it up, a little bit of charge, let me use the little thing here. A little bit of charge compared to the whole charge is like a little bit of area for one ring compared to the whole area for the disk. Okay, that's what we're going to do. Well, the pi's cancel out, right? So our little bit of charge dq is just going to be 2r dr over big R squared. All right. But what we really want, right, our B, our magnetic field that we're trying to find. By the way, we know the magnetic field from before. The field due to a loop is going to be along the z-axis. So really, I'm just doing the magnitude of the magnetic field. I already know that it's going to be along the z-axis, right, in the z direction. So I won't worry about the vector part. Okay, so this is going to be, I just want to integrate dB, right? So if I'm going to integrate this, I need to relate dq to di. What's the relationship between q and I? So the way it works is, remember, we're not quite ready for that. Let's say a little bit of current what is current? Current is just going to be a little bit of charge that goes by in a unit time, right? It's charge per unit time. So I don't know what to call it, t, the period, right? How much charge goes by in a certain amount of time, t. Well, if I'm just watching this thing spin, then in one revolution, in one rotation, the full dq of each ring goes past, right? So di, the amount of current that goes by, is going to be the charge divided by the time it takes to go all the way around once. And t is just equal to the frequency, 1 over the frequency, how many times it goes around per second, and that's kind of what we're after. So that means that di, which way do I want to write it? Di is equal to n times dq. Well, really, let's say this. The frequency times dq. And the frequency is n rotations per second. Sometimes I've seen in some places, sometimes they call it f, the frequency. Sometimes they'll call it little n rotations per second. But whatever, they mean the same thing. So di is n dq, just the number of rotations per second times dq. Okay. So I think we're pretty much ready, right? So our magnetic field, at least we're ready to write down what the magnetic field is. The magnetic field is going to be the integral. We're going from 0 to big R. dB, okay, so this is going to be mu naught. It's going to be our di. Let's see, di is n dq, so I'm going to have an n. And my dq is 2r dr over big R squared. All right, so that's my di, and then I'm going to have another r squared times r squared, and then I'm going to have another 2 times z squared plus r squared to the 3 halves. So if I write it all out, I have something like this. Oh, and I forgot my, oh, look what I forgot. I forgot my Q. I need to have my big Q in here times Q. I need to add that back in. Okay, let's see. Do I have everything? I got my dq, r squared, 2r. Okay, let's see what this simplifies to. So the magnetic field is, the 2's cancel. So I'm going to have mu naught n q over r squared, and then 0 to r, and then I'm going to have r cubed dr, and then on the bottom I'm going to have this business. We've kind of almost seen this before. This is going to be our z squared plus r squared to the 3 halves. Okay, I think I have all the factors in there. So that's the thing that we want to integrate. The trick is to try to figure out what this integral is. We've seen integrals like that before. Oh, one thing we can do, we can solve one problem right away. What if z is 0? What's the magnetic field there right at the center of the disk? Actually, that turns out to be really easy. Look what happens. If z is 0, we can figure that out right now. If z is 0, then the magnetic field is mu naught n q over r squared, and this is going to be 0 to r. If z is 0, then I have on the bottom, the z squared goes away, and I just have r cubed over r squared to the 3 halves. That's r cubed, right? So this is just going to be the r. That simplifies way down. That's just going to give a big R. So if z equals 0, the magnetic field is just mu naught n q over r. Neat. Okay, well, we've solved one thing. we got that down. So the magnetic field at the center of the disk is going to be just that very simple, just that very simple thing. Okay, so let's go find out what it is for a general z, a z above the disk. So what I'm going to need to do is let's copy this over. Let's see, can I do this? Can I do this? Can I take this? Copy, and then I'm going to paste. Oh, fantastic. Look at that. Comes right over. Okay, so let's put it where we can see it. And there we go. All right, so here's our integral. How are we going to solve this in general? I think what I'd like to do, the first thing, is to try doing a substitution, just a regular u substitution. So let's let our u be this thing in the bottom. This is usually the way we do it, z squared plus r squared. So our du is just going to be 2r dr, because what I'm after is to get something something over like u to the 3/2 on the bottom. Well, I've kind of got that. Look, that'll make the bottom u to the 3/2, no problem. And up top, do I have a 2r dr? Well, sort of. This thing, look what this is. This is r squared times, oops, r squared times r dr, right? And I've got my r dr there, so r dr is just du over 2, and I have my r squared. So r squared is just going to be u minus z squared. So let's substitute that stuff in. I think that'll be something that we can solve. So this is going to be mu naught nq over r squared. This is going to be 0 to r. All right, so this is going to be, let's see, u minus z squared, and then I'm going to have a du, and then on the bottom I've got my 2, and I've got my u to the 3/2. I think all that is just fine. So that's going to be mu naught nq over r squared, and so the first integral is going to be 0 to r. The first one is going to be, let me bring the 2 outside. The first one is going to be u over u to the 3/2, so that's u to the minus 1/2 minus z squared u to the minus 3/2 du. Okay, so it breaks down into a couple of integrals, but those are pretty easy. What's the integral of, let's see, I've got my, again, mu naught n q over 2r squared. What is, oh, and by the way, again, when I do u substitutions, I like substituting the thing back in before I do the limits. So hopefully nobody's yelling at me that I should have changed my limits 0 to r, because those aren't the limits anymore once you make a u substitution, but I don't care. I'll do it later. Okay, u to the minus 1/2, what is that? The integral of that is u to the 1/2 over 1/2. So it's 2 times square root of u. Neat. And then I'm going to have a minus z squared. What's the integral of u to the minus 3/2? Well, it's u to the minus 1/2 over minus 1/2, right? So that's going to change that to be a plus, and there's my extra 2, and then I'm going to have over square root of u. And then finally, when I put this stuff back in, I'm going to have my 0 to r. Okay, so what's nice is that all these 2's are going to cancel. So let's write what we've got. I've got my mu naught nq over r squared, and then I've got. Let's put in what u is. It's square root of z squared plus r squared, and then on the bottom I'm going to have, or the next term is going to be a plus z squared over this same thing, z squared plus r squared. Okay, and now it makes more sense that this goes from 0 to r. All right, so let's do it. Mu naught n q. We keep dragging this thing around over r squared. When I put in a big R, I'm going to have square root of z squared plus r squared plus z squared over z squared plus r squared. Okay, and then I'm going to subtract off what happens when I put 0 in. When I put 0 in for r, I'm just going to get, let's see, what, square root of z? Square root of z squared, z. And then the second term, I'm going to have z squared over square root of z squared. So it's just going to be a z again. So I get 2z. So it looks like this is going to be minus 2z. All right. Oh, here's another thing we can do just to simplify it. Look, what would happen if I took this term, take this first term and multiply it by a 1, and in this case, just to get a common denominator, multiply it by the square root of z squared plus r squared. So that would mean I'd have another square root down there, and then up here, I get rid of the square root. All right, so it would look like that. And then those z's, I can combine those fractions together, and the z's combine together, and you get this, mu naught nq over r squared. It looks like I have 2z squared plus r squared, oops, get my 2's and z's mixed up. 2z squared plus r squared over z squared plus r squared minus 2z. There we go. And really, that's it. So here is the magnetic field along the z-axis, some distance z away from the disk. I mean, that's kind of it. We can simplify it a little bit. Sometimes you might see it where instead of that n, which is the frequency, right, number of revolutions per second, sometimes you'll see it in terms of the angular frequency, omega. Instead of q over r squared, they might write it as a sigma, that surface charge density. So just for kicks, let's rewrite it. We can just do that up here. N, let's see. N is equal to the frequency, and that is omega divided by 2 pi. That's one thing that we can do. And then q over r squared, sigma, is equal to, sigma is the charge per unit area, right? So it's like the charge divided by pi big R squared. So I have q over r squared, so this is going to be like, so this quantity, mu naught nq over r squared, that just turns into, let's see, that's going to be a mu naught, let me write, sorry, let's write it down here because I'll run out of room. This is going to be mu naught n is going to be omega over 2 pi, and then q over r squared is sigma times pi, so it's mu naught. So another way to write it, we could call this mu naught omega sigma over 2 times this business, 2z squared plus r squared. Z squared plus r squared minus 2z. Okay, that's just another way to write it down. Because often we instead of n times per second, maybe you'll see it as angular frequency, and often instead of the charge and the size of the disk, especially if it starts to get infinite, we start talking about the surface charge density. So anyway, it's just another way to write it down. And it doesn't affect what's inside the brackets anyway. So this is another cool application of integrating current loops. Instead of stacking them to do a solenoid like before, this time we just swept out a disk. So when you spin a charged disk, you get a magnetic field along the axis, and this is what it is. Very cool.